that we use to derive materials model, to derive mathematical equations describing the stress strain response of materials. So there are 6 steps, and then the main objective is in the number 6, that we can come up with the stress equations. So it is, we have seen it is the stress is equal to F times L, the length, where F is the force per unit of volume. So the unit is in Newton per meter. And then if we go backward from number 6 all the way to number 1, okay, so in order for us to be able to write a proper mathematical equation for the stress, we need the mathematical expressions of F, okay, in number 6. And then backward step to number 5, F, or force per unit of volume, can be determined from the differentiations of the Helmholtz free energy with respect to the deformations or change of length. And then since we are dealing with rubber materials in which elasticity is entirely caused by the change of entropy, we have learned this. So the change of free energy with respect to deformations is simply given by minus T ds over dl. The T there is the absolute temperature. S ds over dl means that this is the change of entropy per unit of volume with deformations. Okay, so which can be means that minus T delta S delta L, which basically means that we need to evaluate how the entropy of the system, the entropy of your materials will change with deformations, delta S over delta L, okay? And then how we get the change of entropy of a materials with deformations, knowing that rubber consists of many polymeric chain. So what we need to do is that we need to know what is the change of entropy in one single chain in the materials, so that the total change of entropy is simply the sum of the individual change of entropy with deformations as given in number 4. Okay, so delta S is simply the sum of the change of entropy of each individual polymeric chain. Okay, so delta S equal to sigma delta Si, where delta Si is the change of entropy with deformation in the single chains as given in number 3. Okay, so how do we get this entropy? Okay, so entropy, thanks to Boltzmann's equations, can be related to the molecular conformations of the polymeric chains, to the shape. So the level, in the simple word, the level of disorder of the polymeric chain can be related to its shape, its conformations, and this is given through Boltzmann's equations. Okay, which means that in order for us to use the Boltzmann's equations relating the molecular conformations or molecular shape in a single chain to the entropy as given in number 2, then we need to move backward one step. We need to be able to describe the molecular shape of a single chain. Okay, so we did not go into the details step 1 to 3. It requires basic knowledge of statistical mechanics, and I will not go too much into that detail. So I showed to you only last week number 4 quickly, number 5 quickly, number 6, so that we understand how the step was done. Okay, more specifically, we focus on the special case of Gaussian distributions. Roughly speaking, it means that we are dealing with highly coiled polymeric chains. I have shown to you about the conformation last week, showing the shape of one single chain. In Gaussian statistical theory, it is assumed that the distance between one end to another end is very small with respect to the whole length of the chains. Maybe I need to go back here. just to show to you what I'm talking about. This one, okay? So in Gaussian statistical theory, actually, we are focusing on the special situations in which, if this is the conformations or the shape of one single chain, then the distance between one end of the chain to another end of the chain is much, much smaller than the whole contour length of the polymeric chain. Which means that basically, from microscopic standpoint, we only deal with the small strain situation or moderate strain situations. Okay, so this is Gaussian statistical theory. Again, I will not go much into the detail of the statistical mechanics. So with these assumptions, then it leads us to the expressions of the Neo-Hookean models, where we have the expressions of the free energy associated with the Neo-Hookean model. Okay. Noting that for a special case where the deformations occur at constant temperature, which is the focus of our work, then the free energy and the strain energy has the same meaning. So either I say free energy or strain energy W, we are referring to the same thing in this lecture. Okay. So we have done the calculations using the Neo-Hookean strain energy, how the expressions of engineering stress, how is the expressions of true stress. So we have done that, right? And then we have also observed that when we use Gaussian statistical theory, then the applicability of the mathematical equation is only limited to moderate strain up to lambda or stretch equal to 2.5. Okay. Beyond that, we need a better theory, and then this is provided by non-Gaussian statistical theory. And we have seen last week a number of examples. More specifically, I have shown to you an example of non-Gaussian statistical theory, which is 8-chain models or Aruda-Boyce model. And then we have seen the performance, which is, if I go back here, comparisons between Neo-Hookean model and Aruda-Boyce or 8-chains model. So we see that the mathematical predictions as compared to the experimental observations is well predicted by the Aruda-Boyce model, but not so much for Neo-Hookean. So Neo-Hookean is only for lambda up to around 2, okay? The stretch of 2, right? So at the end of last week discussions, I asked you which one that we have to use when we design, when do stress analysis for practical purpose. Obviously, Aruda-Boyce give you much more accurate result, but it involves much more complicated mathematical equations, which means that in the computer, you will need much longer computational time as compared to Neo-Hookean. So it is better that we look at what specific application we are looking at, what is the range of deformations at that particular applications, and then we decide. If the range of deformation is relatively moderate, up to lambda equal to 2, for instance, then it will be enough to use Neo-Hookean. But if the components are really subjected to loading so that it has to deform beyond 2, for instance, all the way 4, lambda 4 or lambda 5, then we don't have any choice. If we want to have an accurate stress analysis, then we need to use Aruda-Boyce. Okay, if we use Neo-Hookean models, we need one parameters, which is G, shear modulus. So you need to find the shear modulus from the experiment. In the same way as when you do tensile test for metals, you need to find Poisson ratio, you need to find elastic modulus to do stress analysis. Okay, for this one, you need to have shear modulus. For the usage of Aruda-Boyce, you need two material parameters, which are the shear modulus and then also the number of segment n. This R needs to be determined also from experiment. Okay, so depending on which model that you are using during the stress analysis, different models require different number of materials that you have to identify from the experiment. Okay, I hope that is clear as a quick summary of the things that we have seen last week. Okay, so for today, I'm going to look at a different approach, really engineering approach, which is called as phenomenological approach. So this is the approach widely used by engineers when they do design the stress analysis for rubber components. Okay, unlike the physical approach, we do not require to look at the polymeric chain, the conformation, and so on and so forth. Okay, the idea is just simply, can I come up with mathematical equations such that when I compare with the experimental finding, I have a good match, like for instance in the 8 chains model. That's the whole idea, without the need for me to look at the microstructure. Okay, so that's how engineers do it. Since the idea is just to find mathematical equations, can I do it arbitrarily? The answer is no. You still need to respect certain restrictions and guidelines. Okay, so in these situations, the useful guideline is coming from thermodynamics. So thermodynamics give us restrictions on how, and give us guideline on how we should have a form of mathematical equations to describe stress-strain response of rubber materials. So I will then start by looking back the thermodynamic consideration that we have seen in lecture 3. More specifically, recall the first law of thermodynamics. But this time, again, as we have started last week, instead of working with energy, internal energy, entropy, and work, so we deal per unit of volume. So I remove the bar over each of the notations. So du here is the internal energy, the change of internal energy per unit of volume. dq is the change, the heat per unit of volume, and the W is work per unit of volume. Okay, so basically, as the first law of thermodynamics state, the change of internal energy in the system per unit of volume is because of the change, because we supply or we extract heat per unit of volume to the systems, plus because we supply or we extract work per unit of volume in the systems. Okay, and we have since dq equal to tds. Again, ds here is the change of entropy per unit of volume, so all quantity per unit of volume here. And dW means that it is force per unit of volume times dL. Okay, which I can then write F Newton over volume here, dL. Which, because I can change, because volume is the cross sections times L, so F over A is stress. Okay, sigma. dL over L is d epsilon, which is the strain. So F small f dl, which is also equivalent by writing sigma d epsilon. Okay, sigma is stress, d epsilon is strain. Now, by recalling back the change of Helmholtz free energy that we have done in lecture 3, replacing the terms dW, instead of using this, we use stress here. Then, in the same way as what we did in lecture 3, we come up to consider equations if we focus on the stress for a constant temperature, which means that dT here is equal to 0, then I can get that sigma simply differentiations of the free energy with respect to strain. Or if it is 3D, then the stress tensor you can obtain by differentiating the free energy with respect to strain tensor. So which means that from this thermodynamic consideration, it gives us indications that if I want to develop mathematical equation to describe stress response of materials, I just simply need to specify what is the free energy, the functional, the mathematical expressions of free energy. After that, I differentiate with respect to strain, I get the expression of the stress. As simple as that. This is how thermodynamics give us a guideline. Okay. If you have any questions, please let me know, or you can also put in the chat box there. Yeah. All right. So some remarks. I will go slowly here. Again, the thermodynamics give us informations, help us, okay, by telling us from these expressions that the stress tensor can be obtained by differentiating the free energy or the strain energy, because we are working on the constant temperature, with respect to the strain tensor. This is what the theory gives us from the thermodynamics. Okay. Now, from the experimental standpoint, what we observe is that rubber materials is capable to undergo large elastic strain. So as we have discussed last week, rubber is capable to be stretched 2, 3, 4 times of its initial length, but the deformation still remains elastic. Okay. And then we have seen also last week that when we deal with a material such as rubber, which are capable to undergo large strain, the more we stretch it, the more the length, the more the contractions that we have in the cross sections. Meaning to say that the more we deform the materials, the more we have reductions in the form of cross sections. And then consequently, what we know is that, as we have also shown last week, is that when we compare and calculate true stress and engineering stress, the value will be significantly different. So this is something important when we do stress analysis with rubber materials. For rubber materials, the deformation that we are focusing at remains elastic. But even if the deformation elastic, we need to choose properly when we talk about stress. If you say that the stress in materials is, for instance, 10 megapascal, then the information is not enough when we deal with rubber. You need to specifically mention, are you talking about engineering stress or are you talking about true stress? Because the two could be significantly different due to large deformations. Unlike in the case of metals, in metals, when we want to maintain deformation remains elastic, we need to maintain the stress below yield strength. And what happens if you observe the deformation? The deformation is very, very small. The elastic deformation is very small. Since the deformation is very small, the change of cross-section is also very small. So either you calculate engineering stress or true stress, the result will be more or less the same. So there is no point to specify true stress or engineering stress when dealing with elasticity in metals, because the value will be more or less the same. But for rubber materials which are capable to undergo large elastic strain, we need to be careful. There are a number of ways that we express the stress. Is it true stress? Is it engineering stress? Or is it other ways of stress measurement? The same way in the strain. Are we talking about true strain? Are we talking about engineering strain? Or are we talking about other way to measure strain? So here is the things which are new. When we deal with such materials capable to undergo large strain, the way how we express stress is not unique. So you can express stress through stress, engineering stress, through strain, engineering strain. There are actually many other ways or many other types of stress. Beside through stress and engineering stress, there are other types of stresses. Beside through strain and engineering strain, there are different types of still much more different types of strains measurement. Okay, so here when we derive or develop mathematical model, we cannot simply write stress as a function of strain arbitrarily. If we choose one stress, for instance, true stress, then we need to pair it with other strain, which is, for instance, true strain. And then we cannot simply mix engineering stress with true strain, for instance. So it is given by thermodynamics. I will not go too much into the detail, but when we write the mathematical equation for stress and strain in large strain like rubber, they have to be paired from the thermodynamic standpoint, and it is called as energetically conjugated. Okay? And then this is developed more in the continuum mechanics. Before I can go to the discussion of how we derive the equation for the stress using phenomenological approach, I will need to give a very brief and basic introductions of continuum mechanics, especially introducing to you how we measure strain when we deal with materials capable to undergo large strain. Okay, so for today, it may be slightly shorter lecture. I will focus on introducing to you various strain tensor that will be useful, that will be used extensively later when we develop the mathematical equations for hyperelastic response. Okay, so here in the next few slides, I will introduce few stress and strain tensor, especially strain tensor, okay, that will be used to develop a mathematical equations later. So I will go slowly. If you have a questions, please interrupt me, or again, you can always type in the chat box. But I would like you to follow every single step to make sure that you understand what is the physical interpretations of each measurement of strain that we are going to discuss. Okay, so the very first and basic measurement of strain is basically the way how we describe change of shape, is the deformation gradient tensor. This is the basic fundamentals way of measuring the deformation in the materials capable to undergo large strain. Okay, so here I give you example of a potato, and then imagine that I can squeeze, deform, and so on and so forth, such that this potato distorted and deformed to becomes this one. Okay, so this is initial potato, and then after that I squeeze and so on, just load it mechanically so that it becomes distorted and having the shape. So it is deformed basically. Since I want to understand the deformations of these materials, then I draw here, before I deform it, I draw vertical lines and also horizontal lines in the potato. And then from here, when the potato is deformed, then I can trace how each individual line will become after deformations. So this is the illustration how the lines become after deformations. Okay, so one line which is initially straight line can become a curve here. Okay, depending on the nature of deformation, so it will not remain a line. However, this is important to note, if the way how I draw this to have a very narrow and small, for instance, square here, if I have many vertical line and many horizontal lines, such that if I consider one element here, it becomes very small, then what will happen is that the line, it's here, for instance, if I consider these elements, okay, I have this line, I have vertical line. This vertical line become curve. And then if I consider this square, then it becomes distorted like this. However, if I make sure that the distance of vertical line is very small, the distance of horizontal line very small, so that I have a very small square, then what I will have here is that the square will not be distorted, it will be simply rotated because it is very small. Okay, or similarly, if I consider one line here, this is vertical line, portions of vertical line here, it becomes curve here. If this vertical line is very, very short, infinitesimal short, so what happened here in the deformed state, it will be also short and it will not be a curve, but simply rotated line. So this is if we imagine that the length of this one is very small. And this is the basic idea of how we do evaluations of deformations, is that we imagine that I have a small line here, vertical line that I call as vector dx. The x is capital. And after deformations, because this is very small, it will not be distorted to become curved. It becomes only rotated. And then the vectors, initially dx bar here becomes dx, but dx becomes small. The difference is that this is the deformed element. This is the initial element. So the idea now, because I want to evaluate the deformations, I need to link between the deformed line here to the initial line there. This is how I describe the deformations. To do that, I need axis. So you can put axis X, Y, Z. So in continuum mechanics, usually we put E1, E2. So we put it number 1, number 2, number 3. Okay. And then let's describe the positions of dx, capital and small dx. So let's say that the vector x here specify the positions of the one tip of this line. And then this point, which is the tip of this line, we change to become this point in the deformed situations. And then the vector associated with this point at the deformed state is small x vector. So from large x vector to become small x vector, right? And then I can link between the two, that the positions at deformed state, I mean the vector corresponding to these positions at the deformed state is simply the vector of the initial positions plus this vector u, which is called as the displacement vector. Okay, so this is the link between capital X vector, small x vector, and then the displacement vector u. Now, how do I link between the small dx here to large dx here? All right. So I will not go into the detail of mathematical differentiations and so on and so forth. I will just jump into the final result, that actually this deformed line can be related to the initial line through this operator, which is called gradient vector x, small x. You have learned in the first year what is gradient, okay? And the quantity of this gradient is actually a matrix 3, a tensor. And this tensor, noted by F, to line here, is called as the deformations gradient tensor. So it is an operator, mathematical operator, which transforms between initial line at the non-deformed state to the deformed state. So the deformations of the line is there in the expressions of deformation gradient tensor. Okay. How do we get the deformation gradient tensor? Well, we need first to determine what is the component of the vector small x here. And the component of the vector small x here will be x1, x2, x3. Component long axis 1, axis 2, axis 3. And the component long axis 1, of course, will depend on the coordinate of large x1, large x2, large x3. Why? Because this point is the deformed positions from the point initially located here. Okay, so how do we get the deformation gradients? This is the definitions of gradient operator that you have learned in engineering mathematics. Okay, so it is a matrix 3, This is the notation given: x11, x1, comma 1, x1, comma 2, x1, comma 3, and so on and so forth. Which means that for x1, comma 1, you need to look at the component small x1 and differentiate it with respect to large x1. For x1, comma 2, you can get it by differentiating the component of small x1 differentiated with respect to large x2. You put it here. Similarly here, x13 is you differentiate small x1 with respect to large x3 initial positions. Which means that you can get the expressions of each component of deformation gradient tensor if you know what is x1, x2, x3 here. Okay. I hope this is clear. Yeah, I'm trying to do it slowly, but if it is still confusing, please let me know. The deformation gradient tensor is very essential quantity when in analysis of deformation of materials. For instance, it gives us not only information on how a line will deform under mechanical loading, but also it gives us information on how much the volume of the potato of the material will change during the deformations. For instance, if I looking at this volume elements, small volume elements, then it will become this one. So the change of volume of the potato, I can predict it from the change of volume of this small element, and then it is equal to J, where J is the determinant of the deformation gradient tensor that I have introduced before. So if you have the information on deformation gradient tensor, you will be able to predict what will be the deform shape of your materials, what will be the volume change of the materials under deformations. And this quantity J, determinant F, is called as Jacobians. Okay. All right. This is the basic things. Now I would like to give you an example on how we use it. How can we determine the deformation gradient tensor associated with any specific deformation of materials? And this is given in this example. Okay. So let's say that I have rectangular rubber band. The initial length, width, and thickness are L0, W0, and T0. Is deformed and then such that the length change to become LW while maintaining constant thickness T equal to 0. So this is a specific deformation requirements for this case. Okay, the length change increases, the width decreases, but the thickness remains constant. Okay, so determine the deformation gradient tensors associated with this kind of loading. So this is the illustrations of how the deformations of the materials. Initially, the length is L0, the width is W0, and the length become L, the width become W, while the thickness remains the same. Okay, and then if I have one point, arbitrary point in the initial state, where the point P, for instance, here, the coordinate, initial coordinate is large X1, capital X2, capital X3. Now, after deformation, becomes small x1, small x2, small x3. Okay, which means that in these situations, in order for us to be able to get this deformation gradient tensor, I need to find what is x1, small x1, as a function of large x1, large x2, large x3. Okay. While in the second one, I'll do the same thing. For instance, what is the x2 one? It means that I need to look at what is small x2 and differentiate it with respect to large x1. So this is how we do it. Okay. So I will show you how we can do it slowly here. So if you do observations of how the geometry change, x1, this is x1. Okay. And then this is L0 becoming L. So if I have arbitrary point located at x1 after deformation, small x1 after deformation, where it was located at large x1 before deformation, then I can have a proportionality laws here that the small x1 is simply L over L0 times capital X1. Okay. I hope you follow this one. Yeah, this is purely geometrical considerations. Small x1 is simply L over L0 times capital X1. Okay, which means that basically we have the ratio that small x1 over capital X1 equal to L over L0. Okay. Now, noting that previously we note that L over L0 is lambda 1. So here is direction 1. So it is lambda 1 x1. So we can see here that the small x1 only a functions of large x1. It does not depend on large x2, large x3 for this kind of deformations. Okay. Then we do the same thing for small x2 and small x3. This is what we get. In a similar way, that small x2 equal to W over W0 times x2. And then we define this W over W0 as lambda 2. Again, small x2 looks like, when we look at from here, depends only on large x2. It does not depend on large x1, large x3. We do the same thing for small x3, which is T0 over T0. Why? Because T equal to T0, so it is 1. So which means that small x3 is simply equal to capital X3. So we know now the expression of x1, x2, and x3. Then by using the definitions of gradient, then we can identify the component of the deformation gradient tensor in this way. Okay. So for instance, for this one, I need to differentiate small x1 with respect to large x1. So here for this special case, it is depending only on large x1, so it becomes lambda here. Here I need to differentiate small x1 with respect to large x2, but it does not depend on large x2, so it will become 0. Similarly here, it does not depend on large x3, so it will be 0. If I do all one by one observation, then I can find that this is the deformation gradient tensor for this kind of loading. So this is the component lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, 1. I hope it is clear. Let me know if you have a question. Is there any question so far?
No, doctor.
Okay, good. So I hope it is clear, yeah, for everyone. So next, I will give you another example on how we use the deformation gradient tensor to predict the shape of the deformed shape of materials after deformations. Here, let's say that I have this square element. Okay, it is a 2D element. So, okay, to make it easier for us to imagine. Okay, so the square with the size of 4 to 4. Okay, and then it is deformed by a deformation gradient according to deformation gradient given here. Okay, so this is the square element, initially square element, and then it is subjected to mechanical loading, which is described by this deformation gradient tensor. The question is, sketch what will be the deformed shape of the square. It is initially square. What will be the deformed shape? That is the question. If I deform it using the deformation gradient given this one. Again, x1, x2, this is the axis 1 is the horizontal axis. Axis 2 is the vertical axis in this case. Okay, so how we do it? Well, we use exactly the basic principle on how we can make use of the deformation gradient tensor here. So the deformed line will be equal to deformation gradients times the initial line. That is the clue. Okay, so what we need to do, please make sure you follow this. Okay, and if you have a question, you let me know. Or if there is a mistake that I made in the calculation, you also please let me know. Right? I made mistakes in the calculation and need to update it, correct it. Yeah. So here is the elements that I'm looking at. Let's say that because I need to see how is each line deformed, so I call it the first vertical line on the left is line 1, L1. This is L2. The horizontal one here, L3, and this is L4. So this square element consists of 4 lines, L1, L2, L3, and L4. So the questions, of course, later is that what will become L1, what will become L2, L3, and L4 after the deformations. So here all the 4 lines, L1, L2, L3, and L4, we can represent it by a general vector in the form large X. Why large X? Because this is the initial state before the deformation. This is the notation used. So it is a vector x1, x2, x3, the component. Noting that we are dealing with the plane where the axis perpendicular is 0. So I just said it is 0. So each of these individual line can be represented by this general vector, x1, x2, and 0. Right? Okay, so this is the representations of each line before the deformations. So what will be these lines after deformations? That is the questions. Okay. So we use the basic principle that the deformed lines is equal to the deformation gradient tensor F times vector, well, the line initial line. Okay. We just simply insert this is the deformation gradient tensor, okay, times the initial line, which I can represent it here because this is the line, okay. So I insert here and I do mathematical operation, a simple matrix operations, and I get this one. So all the lines will be transformed to become this vector, this line. Okay. So all the line which was initially can be represented by x1, x2, after the deformations, it becomes this one. So the next thing is that, of course, I need to check for each of line. For line 1 here, we know that line 1 corresponds to a constant x1 equal to -2. This is -2. Okay? So after deformation, this line 1 will become small x. It is, I simply insert x1 equal to -2 to these equations. Okay, I just insert x1 equal to -2 and I get this one. So the line L1 after deformations will become this one. We do the same thing for L2. What is L2? L2 is a constant x1 equal to 2. Okay. So this one, after deformation, if I insert the value of x1 equal to 2 to the previous equation here, then what I get is this one. So the difference is here is minus minus, here is plus plus. Okay, so we can do exactly the same thing for line number 3 and line number 4. Okay, noting that for line number 3, we have that x2 equal to 2, while for line number 4, x2 equal to -2. Okay, we do exactly the same thing, then we can get the vector for each of the line. So once we have now the equation for the vector, of course, we now need to determine what are the positions of the corner, because the corner will determine the shape. Okay, so what will happen is that actually the reason why I do not also show L3 and L4 is that because we do not need to do it, simply because by knowing L1 and L2, it will be sufficient for us to get informations on what is the point at each of the corner, because this point here belong to L1, this point here also belong to L1, this point here belong to L2, this point in another corner belong to L2. So I just need to look at the equation for L1 and L2 and it will be sufficient. Okay. So first, let's say that for the point 1 in the corner, P1, and also P2 here, the line describing this line 1 is these equations. So now for point P1, the coordinate of point P1 is -2 to 0. So the x2 for point P1 is 2. If I insert this value of x2 to this vector, which means that I get the information where the point will be after deformation, it becomes -3 to 0. Okay, you just simply insert x2 equal to 2 here. So it becomes minus 3, 2, 0. Do the same thing for point P2. Point P2, this is the coordinate. So the x2 of point P2 is minus 2. So that's why I only focus on the x2. That is why I put in red here. For P2, point number 2, then the x2 equal to minus 2. If I insert here, then I have the new point for the location for P2. I can do exactly the same thing for point number 3 and point number 4. Same way. Okay, this is the equations for line 2. Okay, line 2 is x1 equal to 2. So this is the equations. Now, if I look at point specific P3, this is the coordinate. Again, because now I'm focusing on the x2 of each point, so I put it in red. In the first case, it is 2. So after deformation, it becomes this point. And for P4, after deformations, the coordinate becomes this one. Okay, so from that, and now I can sketch that this is how the deformed shape of my materials, of my square elements, after being deformed by certain specific deformation gradient. Is that clear enough? The step. Yes, so I hope all the mathematical equations, I do not do all detail, just some few equations, but I think that it should be enough. However, if it is not clear for you, so please let me know. Yeah. So we know how to learn to use deformation gradient to predict what would be the deformed shape of materials. All right. So in this example, the square elements become this trapezium element. All right. Okay. So this is how we use deformation gradient F. This is to give us informations what we can do with it. Okay. Now, there are so many other ways that we can describe strain. We can measure strain when we deal with materials capable to undergo large deformations. This time, I will not go into the detail, the meaning of each of these strain, which is called as strain tensors. Okay, so I will just take out and then give the final result, the expressions of each of the strain tensor that also used to describe the deformations of rubber. And then you will use it a lot later on when we develop mathematical equation to describe stress. So from the information of deformation gradient tensor F that we have before, we can then determine other strain tensor. For instance, first, what it is called as displacement gradient, which is denoted by H. And it is given by the deformation gradient minus I. I is identity tensor, which means that the component along diagonal all are 1, while outside diagonal are all 0. Okay, so I hope it is clear. So the tensor I is the tensor where the components along diagonals are all equal to 1, while the component outside diagonal are all equal to 0. This is identity tensor, identity matrix. From the deformation gradient tensor, we can also calculate what is called as the left Cauchy-Green strain tensor. And it is given by F times H transpose. So you know how to do transpose of matrix. We can have also right Cauchy-Green tensor here. Engineering strain, so this is what we know as well. Engineering strain is actually half of the displacement gradient plus displacement gradients transpose. We can also have another strain tensor, which is Green-Lagrange. Okay, so basically it is given by this one, engineering strain, plus the second term here, which also actually equal to here half of C minus I. C is the right Cauchy-Green tensor here. I equal to this one, which is identity tensor that I have explained before. We can also have the through strain or logarithmic strain. The proper definition is that with e to the power of 0 here is half of ln c. C is this one. Okay, so these are few examples of how we can describe deformations of materials using different strain tensors that I do not explain in detail the physical meaning, but we are going to use it somehow. Yeah. Okay, so let's have a look how to use it. So please prepare a piece of paper. So I will leave you to do it for 10 minutes and then upload it to the Spectrum. This will be, I think this will be the last one for today. So it will be short. I will not continue to the development of concentric models to make sure that you understand well the basic fundamentals of few basic introductions of strain measurement. Okay. All right, so this is the last part, I think, if I'm not mistaken. This is the example, number 5. Okay, so again, we have a rectangular rubber band having initial length, width, and thickness, respectively, of L0, W, T0. It is subjected to a uniaxial tensile loading. So it is very specific. It is called as uniaxial tensile loading. If rubber assumed to be incompressible and isotropic, determine the following tensors. What is F, what is B, what is C, E, and epsilon. Okay, so what is the difference between this example with the previous example dealing also with rubber band? Here, there is no restrictions of constant thickness. If you remember, in the previous example, the deformations, we stretch it and deformation occur at constant thickness. This one, it is not constant thickness. You only stretch the materials along the length and allow the materials to contract along the thickness and along the width. And then similar, actually, this is example that we did last week, that rubber is assumed to be incompressible and isotropic. So determine the following tensor. Okay. All right, so I will give just one example how to look at it. Again, let's use these definitions. Lambda 1 equal to L over L0, lambda 2 equal to W over W0, lambda 3 equal to T over T0. Okay, and then we use the assumption incompressibility, which means that the volume remains constant. V equal to V0, so L WT equal to L0 WT W0 T0, and then if we rearrange, then we have lambda 1 lambda 2 times lambda 3 equal to 1. So that is from incompressibility, something that we have done last week. Okay, from isotropy we observe that lambda 2 is equal to lambda 3, so we know that now I can express lambda 2 and lambda 3 as a functions of lambda 1. Okay, so here, what can I say here? The more you stretch along lambda 1, the more you have reductions in length and in width and reduction in thickness. That is what this information is given, yeah, from these equations. So with this, actually, we do exactly the example like in example 3 before. Then I can get that F equal to lambda 1, lambda 2, lambda 3, where lambda 2 equal to 1 over square root lambda 1. Lambda 3, here lambda 3 equal to 1 over square root of lambda 1. Now, I have given you the expression for F. You need to find, go back here, what is B, what is C, what is tensor E, what is tensor epsilon from the informations of F here. So I will give you 10 minutes to do this, and then I will open submissions link as usual in the Spectrum. So now is 12, well, let's say 05, and then I will be back at 12:15. Yeah. So please have a look, do it, upload it in Spectrum, and I'll be back at 12:15. If you have any question, you can type in the chat box. All right, so let's have a look for this one. Okay, so I've seen that only 3 of you submit. Okay, so I would like to remind you that I will look at each of the individual submissions of the example, yeah, because there will be contributions from this to your final mark. Yeah, so there is a reason why I ask you to submit actually. Yeah. Okay, so let's have a look for this one. It's very straightforward. You already have the expressions of the matrix or the tensor of F. And then from the previous table here that we have, we can just get easily what is the displacement gradient, what is the left Cauchy Green strain, and so on and so forth for the case of uniaxial extension. Okay, so it's just a matrix operations. So very straightforward and very easy. Okay, because I already helped to get you to get the F. Once you get the expression of F, you just do the matrix calculations. Okay, so from there you can get the matrix B, C, E, and also epsilon. Okay, so what you need to do now, if you look at B and C, it is the same matrix. This is a particular situations. Okay, in the general situations, B will not be the same with the matrix C. It is just a special example. In this particular example, coincidentally, B equal to C. Yeah. This is all the expressions, and then just to have a feeling about the meaning of this tensor. So let's have a look here from F. And then the materials is stretched along direction 1. We impose deformations equal to lambda 1. If you remember, lambda 1 is the ratio between L over L0. So meaning that how many times that we stretch the materials from its original length. If we impose lambda 1 equal to 2, it means that we double the length. If it is 3, we triple the length, and so on and so forth. Okay, so this is lambda 1. What is the meaning of tensor B and C along the direction of stretching? It is simply just the square of lambda 1. What is the meaning of this E? Large E is simply half of lambda 1 square minus 1. And then the easiest things to understand from here is that if we look at the engineering strain tensor, if we impose stretching lambda, then the engineering strain is equal to lambda 1 minus 1. This is, if you remember last week, one of you asked, what is the link between stretch, lambda, and the strain, the engineering strain. So this is the link. Lambda, epsilon is equal to lambda minus 1. Okay. And then the rest is that this is F along the second directions, B equals second direction, and so on and so forth. And this is engineering strain along the second directions. Okay, so as you can see here, the strain along the engineering strain along second direction is equal to the engineering strain along the third directions. All right. Okay, so I'm going to stop here because the following slide is regarding the phenomenological approach that we are going to discuss. Okay, but before that, I think I will just stop here and leave the rest for the next week class. So I will end this lecture now. I will open to the discussions or questions if you have any. Let me know if everything is clear or you have questions. Is everything clear?
Clear, Doctor.
Okay, good. Arunesh, clear. Okay. Deepan Raj, clear. Any other questions?
Everything okay, sir.
Good. Okay, Andre, please go ahead. You would like to use mic or you would like to type? Please go ahead. Okay, this is a very good questions. Okay, so the usage. You will see the usage later more on when we derive the mathematical equation for the stress. So the usage and so on and so forth, keep it for next week. Okay, so you will see more on how we use it first. For the physical significance, okay, in detail you will need to read books. Okay, you need to read books, continuum mechanics books. But the idea is that come to basic principle, what is strain? F, B, C, E, and epsilon are all measurement of strain. What is strain? Strain is the mathematical descriptions of how the shape change in materials during the deformation. So this is just a mathematical expression to describe the change of the shape in the materials. All right. For the case of engineering strain, you know it well. It is easy to grab the idea because you have learned it for so long. It is simply in the case of tensile load, you can imagine it. It is just simply the change of length over initial length. That is the significance of the engineering strain in the case of uniaxial extensions. But if you look at in the more complex situations of multiple loading, so you have strain, and then you ask questions, what is the strain along 1, 2, and 3? It will be a bit more difficult. But the idea is that it is the change of length over initial length that is for engineering strain. So what happened is that for E, the second one here, if you see, if I go back here, again, you need to read more in the books, okay, here. The green Lagrange is the sum of the engineering strain plus this one. If you look at this, engineering strain is the sum of H. This is a linear. If you look at the second part, it is multiplications. It is non-linear. So the green Lagrange is the measurement of strain in the case you are dealing with non-linear deformations. So true engineering strain is a good measurement, but it is very simple one. In the case of large strain involving non-linear deformations, then green Lagrange may be more suitable to describe the strain. Okay, it is also the strain. And then how in the case of uniaxial extensions, it is half of lambda 1 square minus 1. That is from the equations. In the same way that engineering strain is simply lambda 1 minus 1. Okay, so C also from mathematical standpoint is lambda 1, but square. So the idea is just simply you want to quantify the shape change. And then when you quantify the shape change, you can do a multiple of ways. And these are just a few examples that commonly used in continuum mechanics that will be used for our purpose in next week. Again, to go into the detail, to link with, because like F, for instance, F transform line elements before to after. Okay. B later will give you information about the length of the line elements. Not only the line element itself, but the length, for instance. So you need to read in the continuum mechanics. That is something that I will not discuss in detail here. Yeah, but we will use it because it will be used in for the constructions of the mathematical model. So the usage, you will see it in the next lecture. Okay. The significance, you will need to read much more in the books, yeah, to have really a detailed information, to have a real feeling what is the difference, significance between each of these strength tensor. You can look back in the example, for instance, the example number 4. In example number 4, I give you informations on how to use by the information from F. But you can see later on, if we calculate the tensor B, the tensor E, the tensor C, then you can have informations on the linkage between, for instance, this one. Well, if I go back here, the multiple way of how to link between this vertical line to this new line. Okay. So again, I will not detail it much here. We don't have much time to do that. But again, simply that it is a way how we describe the change of the shape in the materials, and it will be used. The usage you will see more on next class. Yeah. Okay. Any other questions? I know that many of the things I do not go much into the detail because we don't have time. Yeah, to go. So that is why in the beginning I mentioned that I only give a very basic introductions of continuum mechanics, especially dealing with how we describe strain in the materials. But a lot more information you can dig from the books. Yeah, a lot of information you can read from the continuum mechanics book. Andre, I hope some of the things is helpful, and then some of the things like usage, please keep it for next week. Yeah. Any other questions?
Doctor, can you upload the last week's lecture and this week's lecture?
The last week lecture. Oh, I haven't uploaded.
I haven't, Doctor.
The video, yeah. Okay, thank you for reminding me. I will do together with the today lecture.
Okay, thank you, Doctor.
Okay, thank you for reminding me. Yeah. Any other remark or comment, questions before we end? Okay, if no questions, I hope it is clear so far. We stop here. I will see you next week, which is next year. So, Happy New Year to all of you. And then I hope in 2021 it will be a much better, bring much more luck for all of us than in 2020. We know 2020 has been a very full of challenge period. Deal with something that we have never dealt previously in our life. Hopefully next year things will get better. Yeah. Again, Happy New Year. Enjoy your long holiday, long weekend, and then I will see you next week. Right? Thank you very much. See you next week.
Okay, thank you, Doctor. Happy New Year.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor. Happy New Year.